This is the third of 3 videos on groundwater. In this one, we're going to talk about aquifers, storage properties, some properties of the subsurface, and how much water it can hold and where it goes. So this is important. If we are working, for example, on a rain garden, and we have the soil down here that the water is going into, we want to know how much water can we get in there, how fast it goes. We can use Darcy's law for that. And then if it's drained, how much comes out. If it's half full of water, how much is in there. So we need to know a little bit, at least, about the storage properties of aquifers or soils. You might have seen some of this in your soils classes. We'll go through the terminology we'll use here. And so I'm going to go through these notes, and then also I have a homework assignment that uses a few other properties, and in the homework assignment you can read the description of it in the problem. All right, so I have a diagram here of a section of the ground. So we have below the water table here, we have saturated formation, saturated rock. So the pore spaces are filled with water. So the pore water is in there. So the water table is along there, and then below that, it's saturated. Above that, it's unsaturated, but there is water in there, and it can be moving down. So a measure, we'll get to the second, of how much water in there is the saturation. And notice it also mentions the capillary fringe here. So capillary forces will, like in a real thin straw, we'll call, because of the surface tension of water, it'll rise in there. That's how trees get water up the tree. Well, the same thing happens in the ground. If you have these small particles and small spaces between them, the water will rise by capillary forces a little above the water table. So it'll be pretty full of water here, but then if you put a pipe in it, it'll settle at the water table elevation. So there's a little fringe there, we call it capillary fringe. So property we need to define is the specific yield. The specific yield is for unconfined aquifers. So for confined aquifers, we have a slightly different, we have the storativity or storage coefficient. And so in a confined aquifer, it's full of water when you start, and then you pump water out, and it's still full of water. What we're dealing with stormwater and infiltration is pretty much always unconfined aquifers. So for an unconfined aquifer, it's full of water when you start, and then you drain it out, that water table, the water level actually drops. So it drains out of it. So we're going to define the specific yield as the volume of water released under gravity drainage from a volume of initially saturated material divided by the total volume of the material. So it's a fraction of the total volume. I mention that because, well, you'll see when we get to the saturation, saturation is a fraction of the pore space. So it's a fraction of the total volume. So for example, if I have a 1 meter cube box of sand, I open it up, the dirt doesn't fall out, but the water drains out. Not all of it drains out. Some is left behind, and that depends on the soil material. If I have gravel with real big spaces, just about all of it will fall out. If I have a clay, it'll just kind of stay wet clay, and just a little bit will drip out. So the specific yield is a property of the material. So it's the volume drained or the volume total. Now the volume left behind, retained with the specific retention, specific yield, specific retention, and the specific yield plus the specific retention adds up to the porosity, the pore space. So if it has this one 0.1 coming out, it has a porosity of 0.3, there's 0.2 left behind, again, fraction of the total volume. So the specific yield will range in, like I said, for clay, it's going to be small, like 0.01, and like 0.3 for a gravel. Let's go through an example here. So I have take a soil core, and I'll say its total volume is 280 cubic centimeters. Now we're going to use a real convenient conversion here. The density of water equals right about 1 gram per cubic centimeters, which is same as 1 gram per a cubic centimeter is a milliliter, or 1 kilogram per liter. If you multiply the top and bottom by 1,000. So that's going to be a real convenient way to go back and forth between volume and weight or mass. So the whole thing is 280, and then I weigh it. It's partially wet, just taken from the field. It's 544 grams. I fill it with water. I weigh it again. It's at 572. I let it drain out by gravity, like I did here with this one. So I can be able to get the specific yield from that. And it's at 532 is left there. And then finally I dry it out completely and I get to 482. So the porosity is the volume of voids over the volume total. So when it's all filled, all saturated, it's 572 grams. And when it's all dry, it's 482 grams. So that's 90 grams. Remember, I can convert back and forth between cubic centimeter or milliliter and gram. So I'm going to put the equal sign about there. 572 minus 42 is 90 centimeters cubed of water was in there when it's all saturated. So that means 90 cubic centimeters is the void space, or the pore volume. We call this, we like that number too, the pore volume. And so the porosity is that, the pore volume divided by the total volume, and the total volume is 280 cubic centimeters. And so that porosity, the pore fraction, is 0.32, 32%. To get the specific yield, I'm going to take it at, when it's all full, again 572, when it's all full, minus the drained weight. So not the dry weight, the drained weight. So it still has some water left in it after I drain it. So it's 532 when drained. Those are in grams. We multiply it by cubic centimeters per gram. And then that's, again, divided by the total. So it's 40 cubic centimeters drained over 280 total. So the specific yield is 14%, or 0.14. So specific retention, remember the specific yield plus the specific retention equals the porosity. So I could have also gotten the specific retention by taking the 532 minus the 482 divided by 280. But since I already have the specific yield, I can just say that the specific retention equals porosity minus specific yield equals 0.32 minus 0.14, and that equals 0.18. Right? 0.18 plus 0.14 equals 0.32. Yeah, okay. The bulk density, also known as the dry bulk density, is the mass of solids divided by the total volume. So I have the dry weight is 482, and we're talking about that's the weight of the soil. So if this isn't some type of core or canister or something, we subtract that weight off. So this is the weight of these are talking about the weight of the soil. It's 482. That's the mass of solids, right? Because there's no water in it. So all there is solids. So that's the mass of the solids. That divided by the 280 cubic centimeters. And you notice these fractions here are unitless. This does have units. So bulk density, or the dry bulk density, rho sub B, we like to use rho for the densities, and that turns out to be 1.72, and it has units of grams per cubic centimeter. And that's pretty typical. Could be 1.4 to 1.8. It varies quite a bit material, but it's going to probably be something less than 2 and maybe greater than like 1.4 or something like that. The solid density is a little different animal. It's the density of the solids divided by the volume of the solids. So the specific gravity of sand is going to be about 2.5. So I'd expect this to be around 2.5-ish. So the solid density is the mass of the solids divided by the volume of the solids, just the solids, not the whole. Everything else above this is divided by the whole box or the whole core. This is just by the solids. Well, the solids, all right, so let me think. The mass of the solids, I'm going to rewrite this. The volume of the solids is going to be the volume total minus the volume of the voids, right? So we had 32% was voids. That means 68% is solids. So I'm going to write it like that. Volume total times 1 minus the porosity. Again, if porosity is 32 is spaces, then 68% or 0.68 fraction is going to be solids. And actually that would be, so I can punch those numbers in there, but if you think of this, this is that's what we just calculated. That's the rho B. I didn't write it very well. The rho B, the bulk density. So this is the bulk density divided by 1 minus the porosity. And that turns out to be, like I suspected, 2.52. And it does have units, grams per cubic centimeter. And finally, the one I want to mention here is the saturation. The saturation is, unlike these that are divided over the total volume, this is the fraction of the voids that's filled with water. And actually, we can have the saturation of water, the saturation of air, the saturation of, if we have a spill in there like we did with the underground storage tanks, we'd have saturation of the gasoline, or we call a non-aqueous phase liquid. But the saturation, we're usually talking about water here. So the saturation, and we can talk about it at the field condition or things. So I'm going to write in here of water. So at the field condition, it weighs 544, and dry was, oh wait, we had drained, we had dry. Oh yeah, so I want to do the dry. So 482. So 482 is 0 with 0 water. So at the field condition, it has 44 minus 482. Again, I'll write my units in here. Cubic centimeter per gram. So that's 62 cubic centimeters. And this is divided by the volume of, not the total volume, but the volume of voids. So that's 90 cubic centimeters. That's the pore volume, or the void volume. So that turns out to be, the saturation is 0.68. The specific yield and specific retention add up to porosity. If I have the saturation of air and the saturation of water, and again, I'm just talking about the saturation of water here, and the saturation of NAPL, as I mentioned before, non-aqueous phase liquid, the saturations will add up to 1. Should I put an I there for the different types of saturation? Here we're just talking about the water saturation, but I thought I'd throw that knowledge in there. Okay, so that's a little introduction to some of the quantities that we need to know to calculate volumes and stuff in groundwater. And look at the homework. And like I said, that one has some moisture content and some different things, but you should be able to reason through from the description of the problem what we're looking for there. Okay.